Hi, everyone, and welcome to our module on enzymes. Most drugs that we use to treat patients work by inhibiting or activating enzymes inside the body. So before we can understand the drugs, we have to understand the enzymes themselves. So enzymes are catalysts, which means they increase the rate of conversion of some biological molecule to another. So the first thing we're going to discuss are enzymatic reactions. And the way to think about enzymes is to picture them as a circle with a piece missing right here. Most enzymes are proteins, but you can just think of them as a circle with a little wedge cut out. And then something called a substrate is a biological molecule that fits neatly into that enzyme. And when it fits into the enzyme, it can form a complex with the enzyme, and then the enzyme converts it into some product P that is useful to the body. And we can write this just like a chemical equation as substrate plus enzyme yields an enzyme substrate complex, which then goes on to form an enzyme plus a product P right here. So the chart that's on this slide here is a classic pharmacology chart showing what would happen to all the different components of this reaction up here over time if we put some substrate and some enzyme in a closed container together. So let's imagine that we had some type of beaker, maybe it's got a little blood in it or some type of fluid, and we put a bunch of enzyme in it and we put a bunch of substrate. Well, at time zero, which is denoted right here, the concentration of substrate would be fairly high. And we would also add some enzyme, that's the blue stuff right here. So there'd be a concentration of enzyme E that we would have right here. And this is what we'd start with at time zero inside our beaker. As we let things start to work naturally, what would happen is the substrate level would fall because the enzyme would begin converting it into product. And that's why you see this red line for the product start to rise right here. And then over time, we'd see a little drop in the enzyme level here because we're forming enzyme substrate complex here. But the bottom line is, as time goes on right here, you see the substrate level fall and the product P level rise, and that should make sense to you because this reaction is just proceeding from left to right. The substrate is going away and the product P is being formed. So now that we have a picture in our heads of how enzymes convert substrate into product, we're going to begin to discuss the kinetics of that conversion process. And the kinetics means how quickly the process occurs. And in order to understand this, we're going to have to do a little thought experiment. So let's imagine that we took 3 beakers in the laboratory. I'm going to draw 3 beakers right now. And let's imagine that we introduced into each one a bit of plasma. So I'm drawing a level here for some plasma inside each of the beakers. Next, we added a known quantity of enzyme to each beaker. So I'm going to write a little E inside each beaker to denote the fact that we've added some enzyme. Now what we're going to do is add substrate, but we're going to add just a little bit of substrate to the first one. We're going to add more substrate to the second one, and we're going to add a lot of substrate to the third one. Now let's imagine that we watched as all 3 of these beakers began to have the enzyme convert the substrate into product, and we measured the rate at which the product was formed over time. What we would see is that in the first beaker here with just a little bit of substrate, there'd be a relatively slow rate of formation of P. So we'd have a slow P formation. It'd be somewhere in the middle for the second beaker, and we'd have a very high rate of formation of P here in the last beaker. And the reason would be that because when we add more substrate, we get an increased speed of formation of the product P. And it turns out that's true for many, many enzymatic reactions. So with that concept in mind, we can talk about what's called Michaelis-Menten kinetics. So Michaelis and Menten were 2 biochemists who worked out the rate of formation of product P as a function of the concentration of S. So they carried out a series of experiments like what I just described, and they plotted the concentration of S on the x-axis here, and they plotted the rate of formation of P on the y-axis here. So the rate of formation of P they called V, or velocity. So that means how quickly P was being formed. It might be moles per minute or moles per hour. They called that the velocity of P formation, and they plotted that on the y-axis and S on the x-axis. And what they saw is that the majority of enzymes follow a nice hyperbolic curve like this that picks up speed, but then plateaus out at some maximum velocity, which they called V max. And it turns out that there's an equation that governs this hyperbolic curve, and this is it right here. It's called the Michaelis-Menten equation. And it says the velocity of P formation V is related to the concentration S by this equation of V max times S divided by some constant called Km plus S. So what we're going to do in the next few slides is talk about different enzymes and how Vmax changes and how Km changes with different enzymes and how they all vary according to the concentration of S as governed by the Michaelis-Menten equation. So let's review a couple of the key features of Michaelis-Menten kinetics that I just discussed. So the first is that adding more substrate leads to more product formation at a faster rate, a faster V, as we discussed on the y-axis of that slide. Eventually, however, you reach some velocity called Vmax that you can't get beyond no matter how much substrate you add. What's happening is that at Vmax, the enzymes are completely saturated. They're doing all they can. So when you add more S, there are no enzymes to bind them and form more product P. Therefore, the velocity cannot get any faster. This means that the only way to increase the velocity beyond Vmax is to add enzyme. And I've illustrated that on this slide here. So the lower curve is system 1, and it's got a fixed amount of enzyme, and it gets maxed out here at Vmax. The only way to go higher and get above Vmax is to add more enzyme to the system so you can convert more substrate into product. So now let's go back to our main curve here and the Michaelis-Menten equation over here. You're often asked on exams to identify Vmax from a curve, and it's very easy to do. Just identify the point where it flattens out and look over here on the y-axis, and that will be Vmax. And remember, that's largely determined by the amount of enzyme you have present in your system. Now what I want to do, though, is talk about the other constant in the Michaelis-Menten equation, and that's Km, which is the Michaelis constant. And Km is different for every enzyme. And now let's talk about how we would identify Km from a curve like this. So in order to understand how to identify Km from a set of experimental data like what I showed on the last slide, we have to understand what this Michaelis constant is. So first, let's look at its role in the Michaelis-Menten equation. Km is in the denominator here, and it is added to the substrate concentration S. This means that Km must have the same units as S. We couldn't add grams plus liters here. That wouldn't be consistent. Km must be exactly the same as S in terms of units for us to be able to add them together. So if we accept that Km has the same units as S, then we should also be able to accept that at some point on the graph, Km must be equal to S. And that's what we want to find, is that point on the graph so we can identify Km. So in order to figure out where that point is on the graph, let's just change Km to S. That's what I've done right here. Instead of writing Km, I've wrote the concentration of S. Now we're going to put this together, and we get 2S on the bottom right here. On the top, we still have Vmax times S because that's the numerator of the Michaelis-Menten equation. Now the S's cancel out, and we have that when V is equal to Vm over 2, then Km must be equal to S. And that's what I've shown right over here. When we're halfway up the y-axis to Vmax, whatever concentration of S that is equal to Km. And this all comes from some simple math of setting Km equal to S and solving the equation. So now let's go back to our curve here. We said that it's very easy to find Vmax. We just look at where the curve flattens out, and that identifies Vmax on the y-axis. And now we can go halfway up, and we've got Vmax over 2. And we follow that over to the curve, and that's going to be a point right here. And we follow that down to the x-axis. And now whatever S concentration we have right here is going to be Km. And this is how you identify Km from a set of experimental data of enzyme and substrate in beakers like what I described before. So that's an explanation of how to find the Michaelis constant from a set of experimental data. But now let's talk about what this Michaelis constant really represents. And to do that, let's look at the Michaelis-Menten equation over here on the right. In order to reach Vmax, Km has to become very, very small relative to S. In other words, S has to be so much larger than Km that we can basically cross Km off and say that the equation is just Vmax times S divided by S. And if that's true, then the two S's cancel and we will be at Vmax. So a very important point for you to understand is the system cannot reach Vmax until the concentration of S is much, much greater than Km. So let's imagine that Km is 0. Well, if Km is 0, then the concentration of S is going to be much greater than Km almost instantaneously. In fact, the concentration of S is almost going to be irrelevant, and the system is just going to operate at Vmax all the time. So when Km is very small, like 0, Vmax is reached very, very quickly. Now let's imagine Km is a higher number, say it's a number like 100. Well, in order for S to get much, much larger than this, we're going to need a lot of S. So when Km is high, like 100, we have to go to very high concentrations of S on the x-axis here in order to reach Vmax up at the top. So I've summarized this on the slide. If you have a small Km, Vmax is reached at low concentrations of S. On the other hand, if you have a large Km, then Vmax does not reach until high concentrations of S occur. Another way of looking at this is if you have a small Km, it means that the substrate binds easily to the enzyme even at low concentrations of S. In other words, even if there isn't much substrate around in the system, that substrate will find the enzyme, bind to it, and form product. Another way of wording this is to say that there is a high affinity of the substrate for the enzyme, and that means you don't need a lot of S around to get to Vmax. On the other hand, if you have a large Km, this means you have a low affinity of the substrate for the enzyme, and you're going to need a lot of S. You're going to need to go very far out on this x-axis in order to reach Vmax when the Km is large. So let's review some of the key points that we've discussed up to this point. Km, the Michaelis constant, is a characteristic of each substrate or enzyme complex and how much affinity they have for one another. The Vmax depends on the amount of enzyme present. And we talked about how you can determine Vmax and Km from a Michaelis-Menten plot of the velocity on the y-axis versus S on the x-axis. Now what we're going to do for the last few slides is talk about an alternative to the Michaelis-Menten plot finding Vmax and S, and that's called a Lineweaver-Burke plot. So in order to understand a Lineweaver-Burke plot, let's review the Michaelis-Menten equation, and I've drawn it for you right here. And now what I want you to do is imagine that we flip it upside down. So instead of V on the left side of the equation, we have 1 over V. That would mean that on the right side of the equation, we would have Vmax times S on the bottom and Km plus S on the top. Well, now what we can do is take this plus sign, which we have on top, and split the right side of the equation into two elements. The first element will be here on the left side of the plus sign. That will be Km on top divided by Vm times S on the bottom. On the right side of the plus sign, we will have S on top divided by Vmax times S on the bottom. And these two S's cancel out. What we can do now is take Km divided by Vmax, which are both constants, and convert that into one constant C, which is what I've drawn down here at the bottom. We now have an equation of 1 over V equals a constant times 1 over S plus 1 over Vm. Now you may remember from algebra that the equation y is equal to mx plus b is the equation for a straight line. So if we plot 1 over V on the y-axis and 1 over S on the x-axis, we now have y equals mx plus b. We have the equation for a straight line right here. And we've just created this by flipping the Michaelis-Menten equation upside down. So now we have what's called a Lineweaver-Burke plot. And this is the exact same data that produced that hyperbolic curve a few slides ago when we put S on the x-axis and V on the y-axis. But now what we're doing is we're plotting 1 over S on the x-axis and 1 over V on the y-axis, and it converts it into a straight line. When it gets converted into a straight line, there are some very important points that are easy to identify. The point where it crosses the x-axis, which is right here, is equal to minus 1 over Km. The point where it crosses the y-axis right here is equal to 1 over Vm. And then the slope of this line is that constant C, which I drew on the last slide, and that's Km divided by Vmax. So what biochemists like to do is take their data, and instead of plotting it in that curved plot like we did before and using the Michaelis-Menten equation, they will instead plot 1 over V versus 1 over S, and now it becomes a Lineweaver-Burke plot. And in this case, it's much easier to identify Vm because it's just the point where it crosses the line. It's easier to identify Km because it's the point where it crosses the x-axis. So biochemists like to plot the data this way. It's just another way of looking at the data and finding Km and Vm. And that concludes our module on enzymes.